In this video, I'm going to be looking at the example with the countercurrent extraction, but doing it a different way. I want you to see that sometimes the choices you make can make the math easier or more challenging, but it's still possible even if you don't choose the easiest way. So let's again look at that example. So we have a countercurrent extraction process shown where we have 0.10 kilograms of xylene per kilogram and 0.9 kilograms of solid per kilogram in a feed flowing at 1500 kilograms per hour. We have a solvent in stream 4 that's pure benzene at 750 kilograms per hour. The mass fraction that exits each unit in the extract stream, so that's the streams 5 and 6, is 10 times that of the solid stream, which is streams 2 and 3. We want to know what percent of the xylene is recovered. So in this case, we're going to do these using units of kilograms per hour for all of these. So we're going to look at flow rates of each component rather than mass fractions. We're going to see that this makes a fairly drastic difference in the way the problem, the math turns out. So I have 1500, and let me turn my pen on, okay. 1500 kilograms per hour in stream 1. 90% of it is solids, 10% is xylene. So I can do that math in my head. And so I have 1,350 kilograms of solids per hour flowing in that stream, 150 kilograms per hour of xylene flowing. The benzene solvent is pure at 750 kilograms per hour, and so I have 750 kilograms per hour for benzene and nothing else coming in there. We are assuming that there is no benzene leaving the extractors with the solids, and we are assuming there are no solids leaving the extractor in the extract stream. So these are assumed values that are reasonable once you have taken a course in extraction. So in this particular case, I want to be able to go through and evaluate all my unknowns. So I'm going to just name this X for stream 2, X for xylene, X for stream 3, X for stream 5, and X for stream 6. These are varying all the time. And then I have flow rates in streams 2, 3, 5, and 6. All of those are unknown also. Now, the amount of solids and the amount of benzene, I can label those as unknowns, S2 and S3, B5 and B6, or I could just take one little quick moment to look and engage logic. So let's just say I'm looking at just the extractor, this one right here. If stream 2 contains no benzene, then all of the benzene that comes in here, this contains no benzene, this contains no benzene. All benzene from stream 5 has to leave in stream 6. Similarly, all the benzene that comes in here has to leave here. Therefore, all of these must be 750. I could also get those by doing balances with unknowns. Similarly, the solids, if they're not leaving in the extract streams, 1,350 kilograms per hour come in here, they must also leave in this stream, leave in this stream. So these are known. Okay? So now then, based on that, let's do the degrees of freedom table. Move this up. Okay, in this particular case, for extractor 1, I have streams 1 and 5 coming in, and streams 2 and 6 coming out. The variables in this case, stream 1, no unknowns. Stream 2 has variables x2 and f2. Stream 5 has x5 and f5. Stream 6 has x6 and f6, so I have 6 unknowns. I can do 3 independent material balances, one for each component. However, the solids and the benzene balances technically are already done. So really what I get is just a xylene balance. Okay? So I already did the other 2 balances, so I'm only left with 1 that I can still do at this stage. Now, sum of x equals 1. Well, this is really in the case where you're using flow rates, not mass fractions. This is really saying the sum of the flow rate. So this is saying, for instance, that 1350 plus x2 plus 0 will equal to f2. This is the sum of x equation for stream 2. And any place where I have an x2 and an f2, I can write one of those. So I have 3 of those equations. Now, what about process specs? Okay, I have process specs pretty much exactly the same way I had them before. In this case, with the new variable system, my process spec for extractor 1 is that x6, the amount flowing out of stream 6, is 10 times x2. So I have 1 process spec, leaving me with 1 degree of freedom. I can do the similar things for extractor 2. My streams in are 2 and 4. Out is 3 and 5. My unknowns are going to be x2, f2, x5, f5, and x3, f3. Sorry, I missed a stream there. So I have 6 unknowns. I've already done the solids and benzene balance, so I'm left with 1 independent material balance. For each of these streams with unknowns, I do have a sum of x type equation, so I have 3 of those. I have 1 process spec. In this case, it's that x5 will be 10 times x3. Okay, so I have 1 of those. So 6 minus 5, again, is 1 degree of freedom. It's not totally specified, but it's getting close. So what about the overall? Well, I have streams 1 and 4 that come in, and streams 3 and 6 exit. Streams 1 and 4 have no unknowns, but I have x3 and f3, x6 and f6. So I have 4 unknowns. Material balances, again, I have the xylene balance that I can still do. I have 2 sum of x equations, and I have no process specs, because although I have 2 equations that relate to, I've got an equation with x6 in it, I've got an equation with x3 in it, both of those will introduce 2 more variables. So if I were to use those as process specs, I would have to add 2 more variables to my list. So again, I have a degrees of freedom is 1. So none of these are well defined, just the same result we had before. But I do have that these are all close. So let's write what these various balances are. And I'm going to emphasize the material balance and the process specs, because those will be the ones that pertain to the solution. So my material balances. For the xylene, I have that X for xylene for stream 1 is 150, okay? And for stream 5 is X5. And streams 2 and stream 6. So this is the xylene balance on extractor 1. Next, let me do the xylene balance on extractor 2. Okay, so that says that X2 plus 0, nothing comes in stream 4, is equal to X3 plus X5. I similarly could do an overall balance. N is stream 1 and stream 4, so 0. Leaving is streams 3 and stream 6. So those are my possible material balances I could write. Along with this, I have those process specs. So X6 equals 10X2, X5 equals 10X3. Now the math looks like it's easier, right? It turns out that it's really exactly the same as what we did doing it the other way, but visually it just feels so much better. I don't have such complicated looking expressions. So again, I can get all of these in terms of, say, X3. So X2 equals X3 plus 10X3, meaning 11X3. X6 is going to be 10 times 11X3. We already have X5 equals 10X3. And so now I can use those to solve any one of these for X3. And I end up with same numbers as before, same results as before. Again, 99% of the xylene will be recovered.